Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome students. Starting with the name of Allah, who is most merciful and beneficent. So in the last lecture we have discussed the sum of the transient responses of second order system, and then we will start our discussion on general second order system. And we have started the derivation for the step response of general second order system. In the last lecture we have done our derivation up to this step, and in the next step I have added and subtracted these two terms. I have do so because I want to make this term a perfect square like this, and also I make omega n square constant in these two terms. So I will get this term here, and in this step I make this term as a whole square by taking an under root on this term here, as you see. So then in this step I break this term into zeta omega n and zeta omega n, and then I separate these two numerator in such a way that these two terms can relate with the formula of exponential cos omega t and exponential sin omega t. So this term is equal to, or this term have the same value, same form as of exponential cos omega t term, but this term has this term is not having the same form as e की power a minus at sin omega t term. So for that I have multiplied and divided by under root 1 minus zeta square term here, and after multiplying and dividing by this term I have made this term as of the same form as exponential sin omega t term. After making them in the form as to compare with these two formula, I am taking inverse Laplace transform so that the output response in time domain will be 1 minus e की power minus zeta omega nt and cos of omega n under root 1 minus zeta square t. And similarly, with having the minus sign and then this constant term here, and then the exponential of minus zeta omega nt and then sine omega n under root 1 minus zeta square root t. So we can write this equation in this form as well, as we have discussed in previous lecture, that by using the relation of cos alpha minus beta we can derive this relation, and in this output response phi will be equal to tangent inverse of zeta upon under root 1 minus zeta square. So this is the step response of the general second order system, and it is somewhat similar to the output response of underdamped system. So now we look on the plot for this equation for different value of zeta. So here it is clear that the higher the value of zeta, the lesser will be the oscillations, and the lower the value of zeta, the more will be the oscillations and overshoots. So up till now we have defined two parameters associated with second order systems, that are zeta and omega n. Now we will discuss other parameters associated with the underdamped response, that are rise time, peak time, percent overshoot, and settling time. So first of all, we discuss the definition of rise time, which is denoted by TR. The rise time is the time required for the output waveform to go from 0.1 of the final value to 0.9 of the final value. So first we define these terms, and then we will look at the plot to understand their physical meaning. Now the second one is the peak time, and it is defined as the time required to reach the first or maximum peak value when our output response achieve its maximum peak value. The third one is percent overshoot, and it is defined as the amount that the waveform overshoots the steady state or final value at the peak time, and it is expressed as the percentage of the steady state value. And in the last, the settling time, denoted by TS, and it is the time required for the transients damped oscillations to reach and stay within plus minus 2% of the steady state value. So now we will look at their graphs. So this is the second order underdamped response specifications. So here we can see that this is the point where our output is 0.1 of the final value, and this is the point where our output value is 0.9 of the final value. So this is the rise time, and for the peak time here, so the peak time is the time when our output reaches to its maximum value. So this is the peak time, and for percentage overshoot, here you can see that this is my maximum value, this is my steady state value, and my output response will increase from this final steady state value up to this point, and then after some time it's settled down here. So this is the overshoot that our output response achieve, and finally for settling time, which is plus minus 2% of the final steady state value. So here we can see that if our final value is 1, final steady state value is 1, so its plus 2% will be 1.02, and its minus 0.2% will be 0.98. So here we see that our response starts and take this overshoot here, and then gradually it settles down over here. So when it is settling down here at this point, the response will not cross this plus minus 2% values. So we said that this point is our settling time. So if this response will go further from this point and cross this plus 2% value, and then it settles down like this, then we will say that this point will be the settling time. So these are the physical representation of these terms, and if we notice that the definition for settling time and rise time are basically the same as the definition for the first order systems. So the rise time, peak time and settling time basically represents the information about the speed of the transient response, and this is information will help a designer to determine if the speed and the nature of the response will give the required performance of the system or not. And now we will evaluate these terms: rise time, peak time, percent overshoot and settling time as a function of zeta and omega n. So first of all we will evaluate the value of peak time. So in this plot, this point here is our peak time, and if we want to evaluate the value of peak time, we have to take the derivative of this output response plot. So by taking the derivative of this plot, we are basically finding out its slope, and we know that at this point, which is our peak point, the value of slope is equal to 0. So first we evaluate the derivative of this graph, and for that we have to take the derivative of the output response equation that we have derived earlier. So after taking the derivative, we put the derivative term equal to 0, so that we are basically putting the slope equal to 0, and the value of slope equal to 0 will be at this point, and also the value of slope will be 0 at this point as well, and the value of slope is also equal to 0 at this point as well. So we will generalize our final equation, and then we will evaluate our answer for only this point, which is our peak point. So here we have the derivation for the peak time. So we are differentiating the output response in frequency domain because it will be easier for us. So here I have taken the Laplace transform of the derivative of output response, and it can be written as this value here. This S is representing the derivative, and this is the equation of our output response. So first we completing the square in the denominator here. For completing the square, we will add and subtract these two terms, and then here we will get this square term, and to make this term square we will use this under root over here in this term. So after making these two terms the perfect square, we are now multiplying and dividing by under root 1 minus zeta square in the numerator, because we know that to make this equation similar to this equation, we have to make the numerator term, which is omega, equal to this omega square term. So we are multiplying and divided by under root 1 minus zeta square to make this term equals to this term. So here we will separating the constant terms, and after that we will taking the inverse Laplace transform to get our response in time domain. So this is our response in time domain, and after getting the time response we will put the derivative term equals to 0 at this point. After putting this value equal to 0, then we have here two time functions, this and this. So we will make both these functions equal to 0, and here we see that the antilog of 0 is equal to infinity, so we cannot evaluate the time term, this term here from this equation, so we will use this term to evaluate the value of time. Here we shift this time term to our right, and then we will evaluate the value of t from this equation. So here I generalized this term with n pi, because as I told you that there are multiple peaks, so to evaluate the time for these multiple peaks, this point and this point, we can use the value of n respectively as 1, 2 and 3. So when the value of n is equal to 0, then the time will be 0, and the output response will be 0 at that time, and when we place the value of n equals to 1, then we will get our first peak, which is our peak time. So now we will evaluate the percentage overshoot term. So the formula for percentage overshoot term is C max minus C final divided by C final multiplied by 100 to convert it in percentage. So here we have two unknowns, C max and C final. So C max is the maximum value of the overshoot, this value, and the C final is our final steady state value here. So for evaluating the C max term, we have to evaluate our output response at the peak time. So the maximum value will occur at the peak time as it is over here. So for that, so we put TP peak time in place of T here. So because of this, every term T, in place of every term T, I have placed the value of peak time. Here here and here, and then after cancellation we will get this value, and in this value cos of phi is equal to -1 and sin of phi is equal to 0. So finally we get this term as our C max value. And if we apply the unit step input to our system, then the final steady state value will be equal to 1. So by putting these value in equation 1 here, C max and C final values, so our final equation for overshoot will be this here. So in this equation it is clear that our overshoot term is dependent on damping ratio zeta. So if we have zeta, so we can evaluate the overshoot term, and similarly if we have overshoot value given in the question, so we can evaluate the value of zeta from this formula. So the plot between damping ratio zeta and percentage overshoot will be look like this. So it is clear from the graph that if the damping ratio is 0, the percentage overshoot will be maximum, and if the value of damping ratio increases, the percentage overshoot value will be decrease. So now we will discuss the term settling time here. So this is the formula of our general second order equation, and we know that the settling time is by definition is the time whenever output approaches and stay within 2% of the final steady state value. So if the final output value is 1, so here I put 0.98, which is basically -2% of our final value. So I can also put here 1.02, which is +2% of our final value. Also here we are assuming that this cos function will be equal to 0, will be equal to 1 at settling time. We are making this assumption because here we have two time terms, this term and this term, and if we have two time terms in the equation, we cannot be able to solve it for the time. So after that, after these assumptions, we will get this value, and if we solve here for t, then I will get finally this value for settling time. So if we put the value of zeta from here in this term from 0.1 to 0.9, then the value of numerator term varies from 3.9 to 4.74. So we can approximate here the value of settling time as 4. So this is the final formula to evaluate the settling time. And now we will evaluate the value of rise time. So we know that rise time is the time required for the waveform to go from 0.1 of the final value to 0.9 of the final value. So to evaluate the value of rise time, we subtract the value of time whenever output is 0.9 from the value whenever output is 0.1. So this is our general second order equation step response. and here we put c of t equal to 9 to get this term here. After solving it, we will get finally this term, and then we put c of t equal to 0.1 in the same equation, and after solving it we will get this term. So here we have two equations and we have to subtract these equations to get the rise time, but here the problem is that these are non-linear equations and we cannot solve it mathematically. So we have to use another technique or any other computer program to solve these equations. So if we want to solve these equations, we have to reduce the number of variables as well, because here we have three variables, omega n, zeta and t2. So here I see that omega n t2, and here also we have omega n t2, and here we have omega n t1, and here also we have omega n t1 together. So we first designate omega n t as the normalized time variable. So through that the variable omega n t1 becomes one variable, omega n t1, and here omega n t2. So then we select a value of zeta and we put that value of zeta in equation 1 to get the value of omega n t1, and similarly here in this equation we put the value of zeta to get the value of omega n t2, and then finally we will subtract these two terms to get the value of rise time here. So we can see the values here. Here when we put the value of damping ratio equal to 0.1, we will get the value of omega n t1 and omega n t2. So when we subtract those values, we will get these normalized rise time. So this is basically omega n of t. So this is the curve between damping ratio and rise time and TR and natural frequency omega n. So we can solve these equations through computer program. I have this program which is written on Python language. So if I run this program here, so we will get the values of the polynomials here. These are the coefficients of the polynomials that will be used to develop the graph of the rise time. So in this program we have followed the same procedure as we have discussed earlier. So these are the libraries, and then I initialize the value of zeta here, and then here I apply the while loop. So this is our equation, first equation, and this is our second equation. So after that we will use this fsolve function to solve these equations. So here I have write both the formula that for rise time that we have in book and the formula that we have developed from that program, and you can see here that these both the formulas are approximately the same. Here I show you this program just to give you an idea that how these non-linear equations can be solved with the help of computer program. Now we have drive expressions that relate peak time, percentage overshoot and settling time to the natural frequency and damping ratio. So now let us relate these quantities to the location of the poles that generate these characteristics. So this is the pole plot for a general underdamped second order system. Here if we apply Pythagoras theorem in this triangle, we will find that the hypotenuse term is basically equal to omega n, and cos of the angle theta will be equal to damping ratio zeta. And here we see that this imaginary part of the pole is equal to omega t and the real part of the pole is equal to rho d. So from these observation, the formula for peak time and settling time can be written as pi over rho d and 4 over rho for settling time. So from these formula it is clear that the peak time is inversely proportional to the imaginary part of the pole, and the settling time is inversely proportional to the real part of the pole. So in this figure, the horizontal lines, these lines on the S plane are lines of constant imaginary part. So we can say that these lines are of constant peak time, and the vertical lines, these lines on the S plane are lines of constant real value, or we can say that we have seen that zeta is equal to cos theta. So these radial lines are lines of constant zeta because the angle will be the same, and we know that the percentage overshoot is only a function of zeta. So radial lines are thus also called lines of constant percent overshoot. So these are the step responses. So in this case the poles have the constant real part, and due to constant real part all the waveforms are following the same envelope and will be settled down at approximately at the same time. They have different frequency but their settling time are same, and in this case if we keep the imaginary part of the pole constant, so we will get the same frequency, or it means that they have also the same peak time. And if the poles are located on the same radial line, so it is clear from this curve that they all have same overshoots. So now we will solve some examples on this topic. So here we have our first example, in which we have given the plot, and in this plot the imaginary part is equal to 7 and the real part is equal to -3, and in this example we have to evaluate the values of zeta, omega n, peak time, percentage overshoot and settling time. So first we find out the value of zeta, and we know that the zeta is basically equal to the cosine theta, and in cosine theta the value of theta can be evaluated by this formula, tangent inverse of imaginary part over real part. After evaluating this term, we will get the value of zeta as 0.394, and from the value of zeta it is clear that it is an underdamped system. So to find out the value of omega n, we know that the omega n is basically the radial distance is equal to this radial distance, and if we find out the value of this distance, we take out the magnitude of this line. How we will do that? By squaring the imaginary and real part and then taking the under root. So here we evaluate the value of omega n, which is equal to 7.616, and for evaluating the value of peak time we have this formula, and in this formula we have two unknowns, omega n and zeta, and we have calculated the value of zeta and omega n. So by putting these values we will get the value of peak time as 0.449, and to find out the value of percentage overshoot, we know that the percentage overshoot is only dependent on the value of zeta, and we know the value of zeta. So by putting the value of zeta in this term, we will get the percentage overshoot as 26%. And also for settling time, we know the formula of settling time, that here this is the formula. So by putting the value of zeta and omega n in this term, we will get the settling time as 1.33 seconds. So this is an easy example. So in this example we see that from the pole plot we are able to determine all the time specifications of second order systems. So now we have another example. In this example we have given a figure, this, and this is a rotational system, and we have to find out the value of J and D to yield 20% overshoot and a settling time of 2 seconds for a step input. So this is a we can say that a design problem in which we have given the two outputs that are overshoot and settling time, and from these values we have to find out the transfer function of the system. So here we first apply the torque equation. Here you know that how to develop this equation, and then we find out the transfer function here. So we have to compare this transfer function with the general second order system transfer function. To compare it with the general second order system transfer function, we have to eliminate this J term, and for that I have multiplying and I have taken common the J term in the denominator. So after taking the J common in the denominator, we will get this term. So now we can compare this term with the general second order system. So by comparing it, we know that omega n square will be equal to k over j. So and also 2 zeta omega n here is equal to d over j here. And we know that we have given two values that are settling time and overshoot. So from the value of settling time we have derived this term, which is zeta omega n, which is equal to 2, and we have derived this formula in the derivation of percentage overshoot. So if we know the value of percentage overshoot, we can easily evaluate the value of zeta. So from this formula we calculate the value of zeta, and from the value of zeta we evaluate the value of omega n here from this relation, and by putting the value of omega n and zeta here we found this equation. And by using equation 1 here, we find the value of j, because the value of k is given in the question, and we have evaluated the value of omega n here. So by putting the value of k and omega n in equation 1, we will get the value of j equal to 0.26 kilogram meter square. And then for the value of d we use equation 2 here, this equation, and in equation 2 there is only one value which we have to put here, which is j. So by putting the value of j, the value of d is evaluated as 1.04 Newton meter second per radian. So in this example basically we have designed the value of j and d, and for that we have given the value of settling time and overshoot. And we have another example. In this example, this is a very simple example. In this example we have given the transfer function, and we just compared this transfer function with our generalized transfer function, and then we evaluate all the time specifications in this example. In this example we have to find the zeta, omega n, ts, tp, tr and percentage overshoot, and we know the formula for all these equations. So first we have to find the value of omega n and zeta, and then from these two values we can evaluate all the time specifications. So here are their answers. So this is the formula for rise time, and we see that the rise time is equal to omega n tr, and after evaluating the value of omega n tr we just cross multiply the value of omega n here, and we find the actual value of rise time, which is equal to 0.078 seconds. So after this example our discussion of the chapter number 4 is completed. So thank you.